from Naber from MIT, and we'll talk about the Ricci curvature, convexity, and application.
Thank you. Okay, so first I'd like to thank the organizers for bringing me out here. It's my first time in Stony Brook, and it's really nice to be out here. And I can chalk. So as was mentioned, the title of the talk is Ricci Curvature, Convexity and Applications. And this is joint work with Kahler. So, I mean, for the most part, like the morals of this talk, most of the results, not quite all, but most of the results really only require lower Ricci curvature. But that being said, most of the results are new, even if you're in, say, an Einstein setting or a Kahler-Einstein setting. So somehow, some of these questions actually are right to study from the point of view of assuming as little as possible. So I mean, I'll state the main theorems in a minute, but maybe I'll give some motivation and describe a little bit exactly what it is we're analyzing. So throughout the talk, we'll be looking at sequences of Riemannian manifolds, say n-dimensional, and Gromov-Hausdorff limits of them. And these guys need to satisfy some sort of lower Ricci bound is all we really require. And one thing I need to point out real quick, because it just appears in a couple of statements and you don't need to understand too much about it, is the fact that associated with each of these guys is sort of a canonical volume measure, a canonical measure. And it's absolutely the simplest thing you would imagine it being. It's just the Riemannian volume measure. So the I is just AVGI. With the exception of the fact that if this is collapsing, so these things are, the volume of balls are getting smaller and smaller, you really don't want this to be a trivial limit. So you normalize it by dividing by the volume of some ball. So this thing actually will limit out to some sort of measure in the limit. And all you really need to know about this guy is two things. And then you can clear your head of the rest of it if you're not too familiar with that. That this measure is maybe not the Hausdorff measure, except in the non-collapse setting. And what's really important about this is that the volume of balls is positive. So if you look at any ball of any size, and you look at this measure applied to it, it's a positive number. So saying that something is mu almost everywhere means dense, from the metric space point of view. If you know those things, you're good to go. Okay. Okay, so maybe we'll start with a little motivation just by asking a couple of questions. So let's even just sort of maybe draw a picture. So in general, we're going to be interested in knowing what sort of spaces can appear as limits. What can appear, what can't appear. And you can just write some down because there may be sort of canonical things that you would like to know. So for instance, let's look at this guy, the so-called horn. It's like a S3 or something like that. So you can imagine how this looks, right? I mean, it's four manifold out here, and it sort of pinches to a single point here, so it's like a needle point. And you can ask, and this appears in Ricci flow and all kinds of things, so this is a very popular space. And you can simply ask the question, can this guy arise as a Gromov-Hausdorff limit of spaces with the lower Ricci bound? Perfectly natural question. And it has two answers, really. So, on the one hand, if you're non-collapsed, so you're assuming there's a lower volume bound here, so that this guy is always bounded below, then the answer is no, it can't occur. And if I don't worry about technicalities here and I lie, I mean, the reason why is very intuitive. And that is, what is Ricci curvature? Ricci curvature controls monotonicity of the volume of balls, right? And so if you pick this point and you look at the volume of the ball of radius r here, as r gets small, well, I mean, so the volume of the ball of radius r over Euclidean space has a monotone quantity, right? And this is behaving in a monotone way, but it's in the wrong way. So this, simply from a volume point of view, this guy can't appear as a non-collapse limit. On the other hand, if we're saying in the collapse setting, this guy can appear as a Gromov-Hausdorff limit, which is unfortunate but true. And these examples go back to Cheeger and Kolding, where you can basically fiber over this guy some larger dimensional sphere and let it collapse in a funky manner. Okay. So that's our horn. Well, what's the next simplest thing to sort of ask about? This guy's understood. Well, let's add maybe a line to it. So here's like a little R piece. So we got like this one-dimensional piece, and we got this four-dimensional piece. And we can ask, can that arise as a Gromov-Hausdorff limit? And actually, luckily, we have actually an affirmative answer to this as well. Turns out the answer is no, it can't. Now, this also goes back to the work of Cheeger and Kolding, but there's sort of a big but about this, and the but is that it relies heavily on the fact that there's a one-dimensional piece here. This is usually where I make a joke about how they say the referee gave them the idea for the proof of this. But he's glaring at me, so I'm going to avoid this. It's written in the paper. Okay, so this guy cannot arise, but it depends heavily on the one-dimensionality of this piece. And now let's just do something really, really silly. Let's just do this guy and maybe cross it by an S1 or something like that. You know, we can call this guy. So this is like a trumpet space, right? I mean, it kind of looks like a trumpet. We can call this a generalized trumpet. Why not? And we can ask, can that arise as a Gromov-Hausdorff limit? And now you'd really, really like to say no to this, right? But this has been unclear, right? I mean, proving that this can't arise as a Gromov-Hausdorff limit is not as obvious, unfortunately. And so one of the main points anyway of the talk today will be that even if you assume Kahler Einstein, something like that, you're fine. I mean, it's not clear. One of the main points of the talk today will actually be to see that it can't arise, that this cannot arise as a Gromov-Hausdorff limit of spaces with lower Ricci bounds. And there's, of course, a more general statement here than just, this particular space can't arise. Well, what's really going on here is you can't have limits that have different dimensions in different pieces. So like over here, this guy was like two-dimensional, once you have that S1 factor, and over here it's like five-dimensional. And that sort of behavior can't occur. Without maybe going into too much detail, let me vaguely state what the more general statement is. So going back to Cheeger and Kolding, there's the following theorem. They say that for mu almost every point in X, so this is a dense subset in particular, that there exists a unique tangent cone at P, and it's isometric to RK sub P here. So the idea is that at almost every point in any limit space under these conditions, the tangent cone is unique and isometric to some RK. So it's sort of locally Euclidean in this sense. But the problem is that this case of P over here may depend on what point you're looking at. For instance, over here, it may be 5 over here and 2 over here, right? Or you can maybe envision some sort of really measure-theoretic, god-awful way in which these things are actually twisted together. And one of the main theorems today will be to get rid of that P, so that we can say there's a well-defined dimension in limit spaces. Okay. Okay, so then let's maybe start moving toward that. So to begin the process of sort of trying to imagine how you might actually prove something like that, to rule out different dimensional pieces, let's just sort of start with what we do know. What I want to start with actually is maybe even looking at Alexandrov spaces, because there's this really, really wonderful theorem by Petrunin, which is quite motivational and really relates to a lot of this, of what's to come anyway. So let's look at a possible limit space where we actually assume it's Alexandrov. And Alexandrov, remember, I won't do a technical definition, but you can pretend like this lower Ricci is a lower sectional, okay? Then you're fine. And then this is an Alexandrov space, so much stronger condition. So let's look at such space and let's take a minimizing geodesic inside of it, some gamma. And you know, this is totally unnecessary, but I'm going to say the length of gamma is 1, just because I'm going to have numbers floating around later, and I don't want to have to make it depend on the length of gamma. Now, what do we know? So there's this result by Bertrand, which is where he proves the Barago conjecture. And what he says is that if we take any 2 points in here, which are on the interior, some P, some Q, and we look at the tangent cone here and the tangent cone here. So remember, tangent cones you get just by sort of blowing up your metric space and taking a limit there. So just sort of the local model for your space. That these 2 tangent cones must be isometric, always. Tangent cones must stay the same on the interior of a geodesic. They can't change. This is almost kind of like saying your singular set's convex, but you know, not quite. So, given that something like this is true for an Alexandrov space, let's just sort of start by asking some simple questions. Let's just start by asking, let's just maybe move ourselves along. And so first question, I mean, are tangent cones on the interior of gamma in a general limit space in this setting? Isometric. That would be really, really nice if this result actually held for limits with lower Ricci bounds or some such. Unfortunately, the answer is no. So let's maybe even discuss a easy counterexample, or silly counterexample. So, silly counterexample. So why should we expect this to not be true? Well, the reason we should expect it to not be true is because it's not even true at a point, right? So there exists a limit space, y, with p and y, such that the tangent cones at p are not unique. So what can we do here as sort of a silly counterexample? Well, what we could do is we could look at x and let that be like r cross y. And then we can let our geodesic gamma just be, your t is, say, t comma p. So over in this setting here, maybe this is what we're staring at. And then over at some point, you know, gamma of, we can even write this as being like gamma of t and gamma of s. Over at gamma of t, maybe we pick one tangent cone. And over at gamma of s, we pick a different tangent cone of y at that point. And now we say, okay, well, the tangent cones aren't unique along the geodesic. Well, fine. But that's just goofy, right? Something felt wrong about that.
So you picked different tangent codes, you mean you're doing different scales when you
That's right, that's right. So, I mean, you ask the question, are tangent cones the same along the geodesic? And to say that the answer can't be right is that you simply looked at 2 different tangent cones at P for this guy, and you compare those 2 at 2 different points along the geodesic. So there are different points in that space. So you pick different tangent cones, and they aren't the same. Okay. But that should feel like cheating, a little bit. I mean, it should feel like, I mean, okay, fine, they're not the same, but you're comparing the wrong tangent cones there, right? I mean, it feels like you shouldn't be doing this. So this is actually good motivation for maybe introducing a definition. So let's actually try to uncheat ourselves and find a way of actually precisely stating how we're cheating. So let's do the following. Let's say X is a metric space. Equal in a space, doesn't matter. With P and Q elements of X. Then we say that tangent cones X sub P and X sub Q So x sub p is centered at p and x sub q is centered at q. And if you don't remember what a tangent cone is, this will give you a definition, so it'll be a reminder too. So we say that they're at the same scale. If there exists one sequence, r sub I, going to 0, such that x with the rescalings centered at p, limit to x sub p, and x with the rescalings centered at q, limit to x sub q. So then we say two tangent cones are at the same scale if they come from the same sequence of dilations. Good. Now, that leads to a perfectly natural question number 2. Well, we've said that tangent cones along the interior of a geodesic can't be constant. Life's just not that good. And now maybe the motivation is, and the next question is, are tangent cones which are at the same scale, so at the same scale, along gamma, or I should actually say in gamma, interior, the same. So now we're asking the same question as before, but we're restricting ourselves by only comparing tangent cones that come from the same sequence of dilations. Now you'd really think that maybe I'm going for a yes here, but actually the answer is still no. Now, on the bright side, we don't have a silly counterexample. So this guy doesn't work anymore, right? Where we just took y cross r, because if you're at the same scale, you certainly get the same thing. This counterexample takes a little bit more work, I'm afraid. I'll just give you sort of an intuitive picture for how it looks. So roughly speaking, what you got to do is you're going to look at sort of the cone over the suspension of some two-parameter family of metrics. So what's that mean? That means here's a cone, here's some suspension, and here's our M. Where our S and T here are sort of parameters depending on the cone factor and the suspension factor. And you can compute out sort of what it has to satisfy to have non-Ricci curvature. So, I mean, what are you staring at here? If you look at the suspension over a smooth manifold, this has two singular points, right? So the cone over it, it has two lines of singular points. So these are your natural candidates as being bad geodesics, right? These are certainly minimizing geodesics. And if you're very careful and you compute out all the equations, you can see that you can get enough extra curvature from this guy that as you move along this geodesic, you can actually force these things to be able to change. So the tangent cone can be unique at each of these points, but it's sort of twisting and bending as you move around it. So in particular, tangent cones at the same scale don't have to actually be the same. Okay. So this is probably feeling like a fairly disappointing talk at this point. We're going to actually near towards an actual answer of something. So there's basically only one thing left to ask now. That is, we've said that they can't be constant along geodesics. We've said that even at the same scale, they don't have to be constant along geodesics. So the last question is or maybe I can even say do tangent cones at the same scale change at some definite rate? And actually the answer is yes. This actually has a yes to it. So yes. So although we can force them to change along geodesics, they can't change in any way we please. So let's write a precise theorem down. So let's let me just remind this setup here. So all we really need here was some, say, pointed sequence. with the Ricci curvature bounded uniformly below. And let gamma be a limit minimizing go geodesic in X. For the sake of argument, again, I'm going to say its length is 1, so I don't have a whole bunch of constants floating around here. But that doesn't matter so much. Then, if x sub gamma of s and x sub gamma of t are tangent cones at the same scale, at gamma of s and gamma of t. If this is confusing you, don't worry about it. Just think tangent cone. I mean, it's a lie, but that's okay. If it's confusing, it doesn't matter that much anyway. For all practical purposes, you don't actually need that usually for most of the applications. So if you have two tangent cones, which are at the same scale, then the following holds. Then the Gromov-Hausdorff distance between, now for the sake of making everything compact, I'm just going to look at the ball of radius 1 inside each of these guys, but that's actually irrelevant. Is less than or equal to some dimensional constant times t minus s to the some power. And actually, let's be a little bit better about this actually. I knew I was missing something. So we really want to look at points in the interior which are pushed away from the boundary, right? So that's the point of being in the interior of a geodesic. So if you're at least delta away from each boundary, delta is anything you want it to be. The point is that you're just going to have less control as you approach the boundary. Then the Gromov-Hausdorff distance between these two tangent cones is at most changing at a Holder rate, is what this is saying. So let's
Sorry, you said the ball of radius 1
yes.
around the...
Any ball is fine, but you just want to make it a compact space.
Right, so but you're looking at the tip?
Yeah, the cone tip, definitely.
Only on the tip.
Only the cone tip. You can look at the ball of radius r on the cone tip if you want a ball somewhere else, right? So I mean, any ball is fine.
If you didn't just want things with a Ricci lower bound, then can these non-uniqueness still happen?
So if you have an upper bound?
No, I mean suppose you had Einstein or...
Yeah, right. So if you have like Einstein, yeah, that's totally unclear. My best guess is no, I can't. But I mean, no one can really crack that. Even at a point, for that matter. Okay, so let's look at some remarks. So, first remark's a little silly, but that's okay. So, at the same scale is crucial. I mean, I already really said this, but I'm just sort of, the point is you have to compare the right tangent cones at these 2 points along gamma. You can't compare any tangent cones you want.
Do the C actually. Yeah. C. It's a
Crucial. But everyone's amused. 2. Alpha of n is, I can just talk 5 times, and it's the first time that's actually been pointed out to me. Alpha of n is essentially 1/2. So what's that mean? Without being utterly precise, I can be precise if you like, but what that really means is that actually, so what's being Gromov-Hausdorff close mean, right? It means that there's a mapping from this guy to this guy, which is, if it's that Gromov-Hausdorff close, it means it's that dense, and it preserves distances up to that much. And now the point is that you can do the following, that this mapping you have between these two guys has the property that for every epsilon, no matter how small you take it, if you restrict it to a subset of this guy whose volume is everything except epsilon of it, then it's actually 1/2 holder, not just this, but with maybe a worse constant, is the point. So it's essentially 1/2. And I'm pointing that out simply because we'll come back to this point in a few seconds. So you can almost pretend like this is a half here.
So you assume non-collapsing always?
No, definitely not. It's not non-collapsing.
So it's just Ricci has lower bound.
Just lower bound, that's right.
So the measure result could be as 0 volume.
What is that?
No. So in that case, you want to look at the limit volume measure, right?
Yeah.
Right. So in that case, it's the limit measure mu, which is not 0. It's a definite measure there. 3. And this is why I pointed out the essentially half, is that this is actually sharp. So what's that mean? So I'm writing that they change at a Holder rate. Now as soon as you write that, you immediately want to sort of ask yourself, well, if it's changing at a Holder rate, maybe it's changing at ellipsis rates. I mean, why should you stop there? And that's not true, as it turns out. So that is, for every epsilon bigger than 0, there exists a limit space, so these are constructed is the point, x of epsilon with some geodesic gamma, such that tangent cones and gamma change at a C1/2 Holder rate, which they sort of have to if you believe this thing is effectively a half, but not C1/2 plus epsilon. So in particular, ellipsis is out of the question. 1/2 is sharp. Four. So there's an effective version from which this immediately follows, and is actually at least as useful. So and that is if instead of looking at some tangent cone at the same scale, centered at gamma of s and gamma of t, we could just look at any ball of radius r where r is sufficiently small, but this is dimensional smallness here. So to say that the Gromov-Hausdorff distance between the ball of radius r around gamma of s and the ball of radius r around gamma of t is less than or equal to some exactly the same thing. C over delta t minus s to the alpha. But now you got to multiply by r because that's the right scaling quantity. So you notice if you have this, you immediately get this by just limiting this guy out. Okay. And let me just make one more. I mean, it's obvious, but it's somehow a good thing just to keep in the back of your head. So in particular, tangent cones at the same scale change continuously. Okay. So given this, let's see how in 3 lines we can at least eliminate the guy that we were talking about at the beginning. So remember what we were asking about in the beginning. We were looking at the following limit space and asking if it could appear. So, you know, a generalized trumpet. Or maybe crosses by S1 or something like that. We asked whether something that looks like that, so maybe it's like 2-dimensional over here and 87-dimensional over there, whether that can arise as a Gromov-Hausdorff limit, a space with a lower Ricci bound. And now let's see that it can't. Well, I mean, this is actually very simple now, right? So let's just take a point here, our favorite point P. Let's take a point over here. So this is in the region where it's, say, 2-dimensional. This is the region where it's, say, 4, 5, 6-dimensional, whatever, something else. And let's connect them by a limit minimizing geodesic. Gamma. Well, what's our contradiction? Well, over here, what are all the tangent cones? Well, this guy's supposed to be, so this is that thing cross S1, all the tangent cones are R2. I mean, they're unique in R2. If we look over here, then all the tangent cones are unique, and say R4. I think that's 5, I guess is what I had in the first guy. Why not? But what's the problem? Well, I mean, right at this point here, it's discontinuous. Tangent cones have to change continuously, and it's not changing continuously. So there's your contradiction. So it can't arise. Okay. So let's maybe even try to now state the actual general theorem from which this is actually sort of stemming from. Well, which is, roughly the same thing, modern definition. But it's a useful definition to write down anyway, so it's as good an excuse as any. Okay, so to understand sort of the more general form of this, that it has to be a constant dimensional element. Let's just sort of make the following. So definition. Let's say that let's define the K regular place. R sub K, which is inside our limit space, as P is an R sub K, if and only if the tangent cone at P is unique and isometric to RK. So this is the collection of points which infinitesimally are k-dimensional manifold points, right? Then that being sort of said, then the more general theorem here is the following. There exists in K such that R sub K has V full measure in X. So in particular, if we could define this as being a dimension of X. Why not? What's that? That's not clear. Yeah, I'm sneaking that one by me. That seems like a reasonable thing to state. The problem is that at a singular point, it's not entirely clear. There isn't maybe something that is looking larger than it's supposed to, so that at these points, this is contributing more than it should, in a certain sense. Seems unlikely, but you got to prove it. Yeah, maybe I'll even go through it real quick. So what's the proof of this look like? The proof of this is roughly a complicated version of the proof of that. So maybe I'll even take a couple seconds. So what's the proof look like? So the starting point for the proof is this result that I see at the beginning that goes back to Jeter and Kohler. So 1, we know that the union of the R sub k's, so this is like from say 0 to n or some such, has V full measure. This was Jeter and Kohler. Two, using something along the lines of a segment inequality, let's see that this implies that for mu cross mu, almost every pair, xy and x cross x, that there exists a limit geo gamma from x to y, right, such that the intersection with this union has full measure in gamma. So, I mean, what's this statement? This is not, I mean, think an Rn if you want. So like an Rn, it's like saying if you have something which has Lebesgue full measure, then that doesn't mean that if you take any line and restrict that set to that line, that is going to always intersect or intersect it well. But for almost every line, that line will intersect it almost everywhere. So it'll be a set of full measure on the line, like a one-dimensional set of full measure on the line. And the point is this holds for, by segment inequalities, this holds for limit spaces with lower Ricci bounds. So given that this guy has full measure, I can say for almost every pair, the intersection of a geodesic between them has full measure as well. And then the last stage is just take two of these guys and assume they have positive measure. And if this is, gets technical, just think that and don't worry about it for 2 minutes and then we'll move on. So take two of these guys with full measure, positive measure. Use roughly this idea here to show that there exists some geodesic gamma such that, let's say, gamma of 0 is inside, well, such that, let's just say at this point, such that gamma intersect R sub k and gamma intersect R sub L has positive measure in gamma. And gamma intersect the union of all these guys. All that items you want has full measure. So what is this? This is exactly that setup over there, right? Just slightly nastier looking version. So at every point, the tangent cone, almost every point, the tangent cone is unique in some RK. There is a set of full measure where it's one RK, a set of full measure where it's some other. Okay, but now we have a continuity. This says at almost every point it's one of a finite number of things. Well, it can only be one of them. You can't have this. So that's your contradiction. It's just that picture with, added nonsense. Okay.
That's it?
That's it. I mean, this is about 3 or 4 pages. But, I mean, all you got to really do with it is, I mean, just show you're in the same setup. That if you got these things with positive measure, then you can pick a geodesic, which I mean, it has to actually lie in one of them. And that's your contradiction.
Sorry, why did you use the Ricci lower bound?
I used the Ricci lower bound in several points. Right? I used it to say that tangent cones at the same scale are continuous, for one. I also use it to say that the intersection with this union here is dense in gamma, define such a gamma. So the point is that almost every point in gamma, the tangent cone is unique in some RK. At the same time, it's continuous, these tangent cones. So that means it can actually only intersect one of these. That make sense? But we assume that we have one that actually intersects both, which you can construct if you have two of these guys with full measure. So it's just about constructing this gamma and then using the continuity of the tangent cone. Was that not at all helpful?
No.
Okay, so what's next? So what's next is so great. We have to find a dimension for limit spaces. I mean, what can you say about the structure of this thing? So we can actually say there's a so-called regular set now, right? But what do we know about this regular set? So that is, we have this set, R sub k, or R sub dimension x if you want, which has full measure, and all the tangent cones are unique in some RK. Now, what is it you might hope to say about it? If this were, say, bounded sectional curvature, a much nicer situation, there are results going back to Fukaya that say that, well, in this context, this regular set, which you could certainly talk about in that context, is a totally geodesic. You take 2 points, look at geodesic connect to them, well, that geodesic is still inside them. This is something that you would like to be able to say in this context. You would like to say the regular set is totally geodesic, so that somehow the singular set is really in this sort of sense being pushed away. And in fact, that can basically be said. To make that precise, there's a slightly weaker notion that actually holds here. And so let's maybe have a couple definitions. So if X is a length space, let's say, with x, y, and x, then we say some curve, gamma sub epsilon, is an epsilon geodesic between x and y. If the distance between x and y differs from the length of this guy by at most some factor. It turns out to be convenient to use this factor, but morally I'm saying within epsilon in some sense, the length of this guy is within the distance. We call it an epsilon geodesic. You can put anything you want over there. It turns out for analysis purposes this is the most convenient notion, but that's not so important. Okay, then we say a subset, U, in X, is weakly convex. If for every x and y in U, and every epsilon bigger than 0, there exists an epsilon geodesic, gamma sub epsilon, which is contained entirely inside U and connects these 2 points. So we're not saying the minimizing geodesic is contained in U, but for every epsilon you can get a curve as close to being minimizing as you want, and it's contained inside U. So what's an easy example? Let's just take the ball of radius 1 Euclidean space, and let's remove the origin, right? Now it's weakly convex. Because we could take this point here and this point here, and we can't connect them with a line here, but we can hop around it by as little as we want. So that's the basic example to keep in the back of your head. That's weakly convex. So in particular, right, the restricted distance function on U and the induced length space metric on U are the same, if you're used to thinking in those terms. Okay, one more annoying definition and then we're good. So also, let's define one more notion of convexity real quick. So if U is a measure on X, and U is mu measurable, then we say mu U is almost everywhere convex. If for almost every, so mu cross mu almost every, xy, and U cross U, there exists a minimizing geodesic gamma between x and y, which is contained in U. So now, again, this is an example of such a thing, right? So in this case, we might have taken these 2 points and said, well, we can't connect that with a minimizing geodesic contained inside the set. But we could perturb it arbitrarily smallly, right? Just move over here and move over here, and now that guy is, right? So again, a ball minus a point, say, is an example of an almost everywhere convex space. So these are 2 notions of convexity, right? This one is stronger in the sense that it holds for every point, but it only insists that epsilon geodesics, so arbitrarily close to being minimizing curves, are contained in it. This holds for only almost every point, but insists that an actual geodesic holds inside. So, 2 competing notions of data convexity. But now, that being said, let's actually get to the point. Corollary. So now we're in the setup again where we have a limit space. We have the regular set, which is going to be R sub dimension, I guess is what I'll call it for the sake of being clear about that. Then we know that this guy is almost everywhere convex. And this guy is also weakly convex. I'm going to skip anything along the lines of a proof because I'm running out of time. So roughly, though, we actually proved this here. I mean, that was actually roughly what this statement was before. So I actually basically proved that for you before. And to prove this statement, you basically do an approximation argument. So you perturb it arbitrarily small for something that actually is contained inside the set with the geodesic, and then you perturb those points a little bit even less to get geodesics between them, and so forth and so on until they converge down. So this guy actually implies this guy after a short argument. In particular, actually, what you can maybe take away from this guy is that the regular set is connected. So I mean, there's an actual topological corollary from this. That's not at all clear otherwise, right? Okay. Yes. So maybe I'll mention one thing. So there is something stronger you can do under bounded Ricci in this case, right? So this holds under only lower Ricci and collapsed and whatnot. But you can also prove the following. So let's pretend like we're in a slightly stronger setup here. So let's take a limit space again, but let's assume two things. Let's assume a lower Ricci bound, an upper Ricci bound, so n minus 1. And let's assume it's non-collapsed. So maybe I'll make this pointed on it. Then the regular set's actually totally geodesic. And 2 minutes or less, sort of, why is that true? Well, if we took 2 points in the regular set here, so by definition now this is a set of points where the tangent cones are in this non-collapse setting, then now take a limit geodesic and restrict it to this guy. We're going to prove open and closeness. Okay, I'm going to do this very quickly. Closeness is exactly the continuity condition. So you have a sequence of points, then by continuity of tangent cones, that guy, this guy, the intersection of this guy with the geodesic must be closed. On the other hand, now it's essentially a result of Anderson and volume convergence that this guy is actually open. Okay, well now the intersection's open and closed. You're done. Okay. Let me maybe state one more application and then squeeze in what I can about actually proving something. Okay, so what's maybe one more quick application of this? So there was this essentially follows from a comment I made a second ago about this guy being connected now. You got to work a little bit harder. I mean, you actually need more of a uniform connectedness, but I won't bother with defining such nonsense. So there was a question that, it was proved by Fukai and Yamaguchi for Alexandrov spaces, and in the non-collapse case, it was proved by Chiger and Coleman. And that is, you're oftentimes interested in the isometry groups of these spaces. So if you look at the limit space, you can ask, what kind of structure do you have on the isometry group? In particular, you would like to say, well, it's a Lie group. Well, like you can for, say, a smooth manifold, something like that. And the theorem, and so I don't know exactly, so Fukai and Yamaguchi proved that is true. This is an Alexandrov space. Chiger and Coleman proved that it is true under the non-collapsed setting in the lower Ricci. And one of the two conjectured it was true in the journal setting, but I forget exactly which paper that goes back to. And so it's simply that. So that is the isometry group of x is a Lie group. And that basically follows from a uniform version of that statement and the work that was already done by geodesics. Okay, great. Let's actually maybe talk about proofs for a few minutes. So we're sort of going back to the beginning now. So now that I've babbled for some time about applications, what all this sort of, I mean, the hard part here is actually proving the tangent cone regularity, knowing things change at a Holder rate. So how do you do something like that? So let's maybe even draw a picture real quick so that we can recall what it is that we're trying to do. Okay, so maybe here's our space x. Here's some limit geodesic gamma. Length can be 1 for the sake of argument. You take some point gamma of s and gamma of t, and you look at balls of radius r around each of them. And we're trying to say that this guy here is Gromov-Hausdorff close to that guy here. Well, what's that mean? That means that we have to construct a mapping from this guy to this guy, which up to the area that we're claiming anyway, is so dense and preserves distances up to that much. We've got to construct such a map. So how might you actually do that? I mean, the proof of this is I mean, it's got the same moral as I guess these things usually go. I mean, there's two things involved here. I mean, we need new estimates, and we need to know how to apply these estimates. So let's even think about this in maybe a slightly simplified situation real quick. Let's even pretend like this is like a lower sectional piece and something, I mean, maybe we've got like an Alexandrov space and everything is nice and smooth and clean. So what might be one way of constructing a mapping from this guy? I mean, let's just start there. I mean, how could you construct a mapping from this guy to this guy? There's sort of a canonical way to do it, and in the Alexandrov spaces it turns out to be very useful a lot. And that is, let's maybe fix this point P here, and let's look at the function, which is the distance function for this point. So, you know, for every point we have the distance to this guy here, which for almost every point anyway, there's a unique geodesic connecting the two. So what you could do is you could just gradient flow by this thing. So if you were to gradient flow by like t minus s, that would map this point to this point, and you would hope it would map this ball to this ball, give or take. If you knew a couple things, so if for instance let's say this guy is smooth, that's a big statement. And let's even do it one further and say that you knew this thing had Hessian bounds. That's a much bigger statement. But if you knew this, then you could gradient flow by this guy, and it's simply a computation that you can take my word for, that these two conditions here would imply that under this gradient flow, that the Gromov-Hausdorff distance between this ball here, so by mapping this guy to this guy, and this guy here, will be bounded by essentially that guy. So it would be bounded by a constant times the absolute value of t minus s times r. So if we knew these two things, we'd be good to go. We could just flow it. Now, of course, this is wrong. First off, why do we know this is wrong? Well, we know this can't possibly, even in some sort of generalized sense, work, because I already claimed for you that a power of 1 here is not possible. So we know something fails here. So there's two things that sort of obviously fail, because I only have really two things written down there. The distance function is not smooth, and it doesn't have a Hessian bound. The not smoothness turns out not to be so much of a problem. You can always sort of imagine looking at a smooth approximation and asking the same question. Maybe there's a function very, very close to the distance function, which is smooth and does have a Hessian bound, at which point you'd be fine. You gradient flow by that guy instead. Still line, but that's okay. More serious, really, is this condition here, which fails. So, how do you fix this? Well, first let's sort of ask what can be said, what's known in this situation, and try to see what's lacking. So let's let H be a smooth approximation to the distance function. I'm being very vague about that statement, except the fact that it's a smooth function, and what we're trying to do is pick something which has as good estimates as possible. So we want the smooth approximation that's close to this guy and has as nice approximations as possible. We know that can't work. What can work? Well, we know from Cheeger and Kohling the following. So what they do is the following. They maybe take this distance function and fix it on the boundary of one of these balls here. And they look at the harmonic approximation. So they look at the harmonic map, the harmonic function in here, which is equal to the distance function on the boundary. And in that case, what they're able to prove is that, so if H is harmonic approximation, then you certainly can't get Hessian bounds, but they prove a nice estimate that looks like the following. So they prove that. What's that mean? This means that, well, on an L2 sense, you have a bound on the Hessian, which is better than scale and variance, but it's not bounded. So what does this tell us? So, I mean, even if we ignore the fact that this thing's only defined on one ball, right? Ignore this piece. And ignore the fact this is an integral bound even. Ignore that. Pretend like this is a smooth bound even. Then what's lacking? Well, I mean, if this were a smooth function and this were a smooth bound that looked like that, then if you flowed by the gradient flow, what it would tell you is that the Gromov-Hausdorff distance between the ball of radius r around this guy and the ball of radius r around this guy is bounded by this. This is somehow not acceptable, right? So if we just use this and try to flow, the problem is that, well, we got a t minus s, and that's great. But if this power of r here is less than 1, let's say epsilon is less than 2, then we can't limit this as r goes to 0 to compare tangent cones. You have to be sharp. You have to be able to actually take epsilon all the way to 2. So the main new estimate is to try to get around that, to take epsilon to 2. Okay, so what's the first problem? The first problem is that's wrong. It turns out that, and by the way, I mean, this may not look familiar, but this is what they prove. And this is sharp in terms of what they prove with the techniques. Like this is some epsilon of n here, that's small and sort of can't be risen this way. And the problem is now that if you work much, much harder, you define new approximating functions and you use very different techniques. The best you can do is epsilon equals 1. You want 2. The best you're going to do is epsilon equals 1 here. So this is like saying this guy is bounded above by r, c times r to the minus 1. Okay, that's still not acceptable. And in some sense that should be clear too, because I already said this can't be a 1, right? So what's the next thing to do? Well, we can't bound this. So what we can maybe do is say, well, maybe we're trying to bound too much here in average. So this was an average over every ball, assuming we did the harmonic approximation separately on each ball. We have a tube here. Maybe you should just be looking at the tube. So instead of looking at the ball of radius r around here, let's just look at this tube of radius r around this piece of the geodesic. Maybe the average of this thing over the tube is better than the average on each individual ball. So maybe, at least for the right approximating function, maybe the average over the tube yeah, I haven't said what h is. H is not the harmonic function. It's a different. It's actually the parabolic approximation. But I'm not even worrying about this at the moment. So maybe that holds. Now there's good news and bad news about this. The good news is that this actually does hold. The bad news is that this is not acceptable. Why? So fine, maybe you can get an approximating function that looks like this on the tube. But I mean, remember our sort of picture that we're trying to rule out, something like this. So that maybe what you're at least imagining happening is that the volume of a ball over here is much smaller than a volume of a ball over here. And if that were true, then although you're averaging over the tube, you're really only averaging over this part of the tube, right? That's not enough. So what turned out to be true that is enough? So what you can do with a different approximation, the parabolic approximation function, is you can say that if you, instead of looking at the average over the tube, if you average over the geodesic all the balls, then that's bounded. And why is this much better? It's much better because if a priori this ball could have smaller volume, it's still weighting it equally. So that's not a problem. And it turns out once you actually know that, you can actually induct something and say that these volumes actually are comparable, but you don't know this a priori. So this is the main estimate that has to be proved. And I'm out of time, so that's where it's going to have to stay, I'm afraid.
Thank you very much for this very nice talk. Are there any further questions?
Yeah, is there any way of getting orbifold points? How you get out the orbifold points in the limit?
From this?
Yeah.
Not really, no. No. I mean, because this thing says that if something, it's only telling you how things change along the interior of a geodesic. Like, you got an isolated orbifold point, you're never going to be in the interior of a geodesic. It does tell you, I mean, you can't use this to prove certain curvature blow-up rates, actually, of Einstein manifolds, which is maybe helpful in that direction, but still not enough.
Any other?
So can you say something about your parabolic approximations?
Yeah, so I mean, there's two natural ways of approximating a function, right? So one here was to look at the harmonic approximation. You fixed it, you looked at the harmonic function. What's the only other natural way of doing it? Well, the other natural way of doing it is to flow by the heat flow, right? And if it turns out the right amount of, so harmonic is like flowing by infinite time, right? In some sense, I guess what it's going to go to. For a parabolic approximation, it turns out if you're looking at the ball of radius r, you should flow by r squared. That's just the right amount. And it turns out that smears out approximating properties much less than a harmonic approximation. And you can get much better errors out of it, though you have to work in very different sort of ways. But nonetheless, that's roughly what happens. It smears less and you get nicer approximations. That's my 40-second version of it.
But so why wouldn't one have thought of this 10 years ago? Or
Weren't smart enough.
Okay, initial data is still the distance function?
Absolutely, absolutely. And in the end, you actually use a gradient flow by the distance function. You use this guy to sort of say that it actually behaves well. You never actually gradient flow by this because this guy can actually pop down to 0 and not actually move by the gradient flow at very small measure of points.
No further questions? Well, let's thank the speaker.